You may remember working double replacement reactions the first time we studied these, and testing different combinations of silver and phosphate with hydroxide or iodide. But let's take a closer look at cobalt 2 nitrate combining with potassium or sodium phosphate. This is the result of the reaction with a blue precipitate. So let's write that balanced equation. Pause the video and see if you can do that yourself. Cobalt nitrate. Nitrate, of course, with its 1 minus charge, we'd need 2. And sodium combining with phosphate. Phosphate with a 3 minus, so we need 3 sodiums to go with it, resulting in the double replacement. We'd end up with cobalt phosphate, and if we pay close attention to the charges, and sodium nitrate, 1 plus 1 minus each. Then you'll need to balance this equation. Anytime we see 3's and 2's, we of course are thinking 6. 3 cobalts, 2 phosphates to satisfy the 2 and the 3. And then that, of course, results in our 6 nitrates and 6 sodiums. We can finish with a 6. Now we want to take a look at this reaction a little more quantitatively. And so we are given 10 milliliters of 0.15 molar cobalt nitrate and 12 milliliters of 0.1 molar sodium phosphate. We want to combine those, allow the precipitation to occur. Consider that if we filtered out and dried the precipitate, what would be the predicted mass of precipitate that should be able to be produced. And then we want to calculate or consider the concentration of all the other ions or all the ions that could be in solution. But you should know that anytime you're given 2 quantities of reactants, this is a limiting reactant problem. So we must figure out which reactant limits. To do that, we'll take our 0.15 molarity times 10 mils. We should be able to do that in our head and get 1.5 millimole of cobalt nitrate. And we can take our 0.1 molarity of 12 mils and get 1.2 millimole of sodium phosphate. Now at this point we don't want to say just the smaller one limits, although that may or may not be true. We need to consider the stoichiometry. We have a trick to do that by dividing each by the particular coefficient in the balanced equation, and we can see without even doing this math that this would result in 0.5, this would result in 0.6, the smaller number, 0.5, telling us that the cobalt nitrate is our limiting reactant. So let's take a look at a picture of this reaction and think about what's happening in the beaker. Cobalt nitrate in one beaker and sodium phosphate in the other beaker. And of course these are both soluble substances. So in the beaker as well, in their initial beakers as well as in the combined beaker, we would have these ions would certainly be separated. Nitrate ions, cobalt ions, phosphate ions. Oops, I can see that I made a mistake on the formula. I wrote phosphite instead of phosphate. Let's fix that. And sodium ions. Now we know that a precipitate occurs, and so our cobalt and our phosphates are ending up down below. Let's write a formula for the precipitate, CO3PO4 phosphate in the precipitate. Now we know already that the cobalt nitrate is limiting, so we can certainly say that all of the cobalt is in the precipitate, whereas only some in the precipitate and some still in solution of the phosphate. Now, because the sodium and the nitrate are spectator ions, we can say that these substances are all in the solution. None is in the precipitate, so we'll label that as the sodium and the nitrate all in the solution. And let's remember that this reaction happens because of a pour together. Remembering that there was 10 milliliters of this substance and 12 milliliters of this substance for a total of 22 milliliters of the solution once they are poured together. Let's go back up and answer some of the questions. What's the concentration of the cobalt ions? Well, according to our picture, there's no cobalt ions in the solution after the reaction, so we can say 0 because all are in the precipitate. That will be true with one of the ions that ends up in the precipitate. Next, we want to consider what about the phosphates. This is probably the most involved calculation of the 4 of them. Certainly the first one was simple. And so at this point we need to say, okay, how much of the phosphate is needed to go with the cobalt to make this precipitate? Remember, it's the limiting reactant that drives that. So we're going to take our 1.5 millimole of cobalt, and yes, we can say cobalt nitrate, certainly, and we want to say that 2 sodium phosphates are required to go with every 3 cobalt nitrates. We can certainly do that in our head. Divide by 3, 0.5, multiply by 2, and so 1.0 millimole of sodium phosphate needed to make the precipitate. Well, if we know that we started with originally 1.2 millimole of sodium phosphate, and really all we care about at this point are the phosphates, but because in the sodium phosphate substance, for every sodium phosphate there's only one phosphate, we can now say, okay, that's 0.2 millimole of phosphate ions left in the solution. All of the sodium ions are in the solution. So we don't want to say that there's 0.2 of the sodium ions in the solution. All of the sodium ions are still there because none of the sodium ended up in the precipitate, but only some of the phosphates are left in the solution. Now, if we want a concentration, that's a molarity, we of course need to divide by 22 milliliters to end up with 0.009 molarity phosphate ions. We use a square bracket to represent molarity of. Let's highlight that, just like we can highlight the 0. Again, remember from the picture that all of the spectator ions, we do not have to think or worry about what's going on with any stoichiometry of the reaction, because all of these spectator nitrates and all of the spectator sodiums are still in the solution. So let's simply go back to how much of each of those are there. So with 1.5 millimoles of cobalt nitrate, 1.5 millimole cobalt nitrate. We don't want to consider the balanced equation at this point. We simply want to say, there's 2 nitrates in every 1 cobalt nitrate. I don't want to go back up and say there's 2 nitrates in 3. That's not true. For every 1 cobalt nitrate, there's 2 nitrates. If I wanted to think about 3 cobalt nitrates, I'd have to say there's 6 nitrates there. But that's 2 for 1. And so that allows us to say, okay, that means there's 3.0 nitrates still in the solution, which, remember, is 22 milliliters, resulting in 0.136 molarity of nitrate ions left in the solution. And so now let's back up and think about the sodiums. The very same thought process. We want to say, there was 1.2 millimole of sodium phosphates. There's 3 sodiums ions in every 1 sodium phosphate. Again, I know it's tempting maybe to look back up and think, but there's 2 sodium phosphates. Well, if we were considering 2 sodium phosphates, we'd have 6 sodium ions. So 3 for 1, 6 for 2. Of course, 3.6 millimole. I can see I didn't say that up here. Millimole of sodium ions, still swimming in 22 milliliters. Maybe it's worth noting that this is total volume, resulting in 0.164 molarity of sodium ions left in the solution. So remember, we do not use the balanced equation when we're determining the spectator ions, but we, of course, and one of the 2 ions that ends up in the precipitate will end up as 0, and one of the ions will involve a subtraction. Put a minus ion here, resulting in the 0.2 remaining.